Right. So yeah. So today I'll speak about. Actually, I will speak about mostly p-adic little conjecture, not mixed little conjecture. But I think for the most of you, it will be fine. So there are not too many differences between them. So I will start with a classical little conjecture, but I won't talk about it at all. Yeah, I just formulate it. So we know where the final problem comes from. A little conjecture. It was posed, I think, in 1931 by Littlewood. And it says that for every pair alpha and beta, or x and y, of real numbers, the following limit as q tends to infinity, q times distance to the nearest integer from q alpha times distance to the nearest integer of q beta equals to 0. So this is a classical standard Littlewood conjecture. I would say it's the most famous conjecture in the Fontaine approximation. So it's still open. There are some advances in it. There are some good results. But as I said, I won't speak about it. I will speak about slightly different problem. So in 2004, Badziahin and Tully proposed another conjecture, which looks slightly similar to this one. Yeah, so Badziahin and Tully. They posed the following conjecture. For every prime p and every real alpha, the following limit q times p-adic norm of q times q alpha, the distance to the nearest integer, equals to 0. Again, q tends to infinity. So they propose this conjecture, and usually now it's called the p-adic Littlewood conjecture. And as you can see, at least it looks very similar. Yeah, so here, instead of one factor q beta, we get a factor p-adic norm of q. Of course, it's not obvious, and that they're very similar, that they should have, I don't know, the same kind of solution if one can find a solution. But I don't know, the practice shows that we have very similar results about both of these conjectures. So for example, if you know that the set of counterexamples has Hausdorff dimension 0 here, then we have the same there. Yeah. Okay, and many people believe that this conjecture should be simpler than the initial conjecture. So one may consider this conjecture as a, like, I don't know, practice, yeah, before the initial one. Yeah, so maybe if we can solve this, it will show some methods which can be used there. But again, this conjecture is also open, so it's open. Right. So what we will do today, first of all, I want to say that not everyone believes in this conjecture. So I know some people, not all of them here, who actually does not believe in this conjecture and who thinks that maybe it's false.
So both ones or only a second?
There is someone else, yeah, who is not here. Yeah. So anyway, if you want to solve it, or if you want to find a counterexample, then first of all, if you want to find a counterexample, you need to know where to look at it. So maybe to look where should one look at to kind of to get a higher probability to find a counterexample. Yeah. Yeah. So today we'll consider several approaches, several attempts where one may try to find counterexamples. In most of them, we'll see that there are no counterexamples. Unfortunately, or fortunately, I don't know. Right. So first of all, some observations. So if alpha is a counterexample to periodic Little conjecture, then since this one is always less than 1, yeah, then we must have q times q alpha is bigger than 0, or in other words, that alpha is badly approximable. Yeah? So if alpha is a counterexample to periodic Little conjecture, then alpha is badly approximable. I will write it. So alpha belongs to the set bad. Yeah. So bad means badly approximable. Or let me define it. So the set of alpha such that they exist positive epsilon for which let me even write infimum. Yeah. Q times QP times Q alpha is at least epsilon. Sorry?
No QP.
No QP.
Oh yes, it's different set. Yeah. Q and Q belongs to positive integers. So it shouldn't include 0, otherwise you get 0. Yeah, so otherwise it's certainly empty. Right, so this set is quite well investigated. Yeah, so we know quite a lot of it. We know how to construct how to describe this set in terms of continued fraction expansions. Yeah, so as I said, we know quite a lot about it. Let me also define one more set related to this, which I usually call bad epsilon. So this bad is a set of alpha such that some epsilon exists. Yeah, but bad epsilon is the same set where this epsilon is fixed. Yeah. So surely if bad is non-empty, then for some epsilon, maybe very small, this set should be non-empty as well. The same thing here. Infimum Q belongs to N. Q times alpha is at least epsilon. Right, and as I said, we can describe this set quite well. And I will do that in terms of continued fraction expansions, and I will use the terminology from combinatoric of infinite words. Oh, here I even don't have combinatoric, just infinite words. Yeah, so if alpha belongs to epsilon, we can describe this set. Then I will denote it by, so this is infinite word, which is combined by the partial quotients of continued fraction expansion of alpha. Yeah, so I probably should explain it better now. Yes. Okay, so I'll write them. on the next line. So then this one belongs to a n, so it's infinite word, where this alphabet consists of 1, 2, n is epsilon to the minus 1 plus 1. So it belongs, well, what I want to say, it belongs to finite alphabet. Yeah, and this is the following infinite word. The following word. So to define it, we just take the continued fraction expansion.
Do you mean the just ceiling of epsilon minus 1? It has to be integer.
Yes.
And then
Integer part. It's integer part. So just A1, A2, A3, and so on, where so it's combined from the continued fraction expansion. Alpha is, so here I don't care about integer part. Yeah. 1, 2, so yeah. So in other words, the partial quotients of continued fraction expansion are bounded by some absolute constant, which depends on this epsilon. Right. So at least the first thing where we should look.
I don't understand. Surely I can change the first 100 digits just as I like.
Yes.
Yeah, sure.
When they write infimum somewhere, yes, here.
Oh, inf is not limit. No. Sorry.
Yeah.
Okay.
Right. So for me, it's more convenient. Of course, we can write liminf, and then we do care only about some tail of this continued fraction expansion. All right. So I have this. Yeah, so if someone wants to look for the counterexamples, then we know where to look at. Yeah, so we should look at badly approximable numbers, or we should look at the numbers which continued fraction expansion has bounded partial quotients. Okay, now let me first give you a couple of known results about it. So the first result is due to initial work of Badziahin and Tilly. They proved that the classical example of badly approximable numbers, quadratic irrationals, they satisfy periodic conjecture. Results. So the first one is due to Badziahin and Tilly. So the same paper as where they defined this conjecture, they show that quadratic irrationals satisfy PLC alpha. Satisfy. So in other words, we know that for alpha, for quadratic irrationals, this continued fraction expansion is eventually periodic. So we know that if it's eventually periodic, then it satisfies periodic conjecture. So this is what they proved. Then slightly later, I don't remember the year, probably 2006, Bugeaud, de Morta, and Badziahin, they generalized it slightly. They showed that if the continued fraction expansion contains arbitrary long periodic parts, then it still satisfies PLC. Yeah. Okay, let me write it here. Bugeaud. De Morta. if this infinite word contains arbitrary long periodic parts, arbitrary long periodic parts, then alpha satisfies.
What does it mean? Arbitrary long blocks which repeat once at least?
Yeah, and sufficiently early.
What does
No,
it
no, no.
mean?
It doesn't actually. It doesn't matter sufficiently early or not. It matters. What does matter that we have arbitrary many blocks. Yeah? So you
What
choose.
does it mean? Just define what it means. Arbitrary long periodic parts.
I didn't want to do that. Okay. So yeah. So you have this word. Yeah. So you have something in the beginning. Then you have somewhere. You have, let's say, u. Yeah, let it be u. So you have an arbitrary many repetitions of the same word. That's my sense.
It's the number of repetitions that gets arbitrary.
Yes. So yeah, if you have this long, very long word u, and once again, and you have only two words, they may be very long, but it's still, in terms of repetitions, it's still short.
Is the same u, or you can change?
In the result, it's the same u. Again, later it was improved. Now it doesn't matter. Right.
Wait, now I'm confused because the arbitrary long periodic parts means it's the same u. Yes, that's what this.
Yes,
means.
but yes, this is what they proved.
Okay.
Yes,
Okay.
this is what they
So what
proved.
they proved is you have some word and it repeats 700 times, or
Yeah.
whatever 100 you say. There's a word that repeats that many times.
The
Yes.
same word, originally the same.
Oh yeah, actually yeah, the quantifier, right? So for every n, there exists a word, but does it have there exists a word that repeats more than n times in a row? Does it always have to be the same word for every n?
In the result, yes.
I see.
Yes, but as I say, later it was improved. Now
see.
it has not. It has not be the same. Yes.
Okay. It need not be the same. I see.
Right. Second result, which I want to mention, it appeared in 2000. I'm afraid I will have to hide some of the previous lines. Second result appeared in 2007, and it is due to Einsiedler and Kleinbock. It actually comes from dynamical systems, so yeah, so it should be of interest for some of you, probably. Einsiedler and Kleinbock. In 2007, they showed that this set of potential counterexamples to periodic conjecture is very small. Yeah? So straightforwardly, from the fact that they should belong to badly approximable numbers, it shows that the Lebesgue measure of this set, because we know that, we know quite a lot about that. The Lebesgue measure of this set is 0. Yeah, so it's already very small. But they show that the Hausdorff dimension of this set is also 0, which is much stronger. Before I write down this result, I want to, because I will use it, I want to write down.
Also for box dimension, like they do.
Yeah.
Yes, this as well. But they actually considered slightly more generalized version of periodic conjecture, and I want to write it down. So they make it more general. Sometimes when you make things more general, it makes proof easier. So their conjecture, so generalized periodic Littlewood. Yeah. again for every p, so it's the same as before for every prime p, prime p, prime. And then they worked not only with one real alpha, but they worked with a pair, alpha and beta. Alpha is real, beta is periodic. Is periodic. Yeah. And for every alpha beta in R cross QP, the following lim inf Q naught tends to infinity, maximum of Q naught times Q alpha minus Q naught times Q beta minus Q naught periodic norm. So this lim inf must be 0 for every pair alpha and beta. So this is the generalization of periodic Littlewood conjecture. So they actually consider this problem instead of the initial problem, the initial periodic Littlewood. Let me hopefully can show you all the lines. Yes. So they consider this problem, and their result is as follows. Their theorem. For every fixed beta, I want. Okay, let me.
Q naught are the same, so it's distance in a fixed Q naught. It's not Q naught in the theorem.
Sorry.
Q and Q naught are both going to infinity, right?
Yes.
But
But
the
I should-
two Q naughts the same in the two absolute values. The difference from the integer and the integer is the same integer.
Sorry. These are the same. Yes.
So this Q naught is the difference of the integer in the real sense, and this is the same difference from the same integer.
Yes. Well, here you look at integers as elements of R. Here you look at them as elements of QP. Yeah. Yes. This number is periodic. This is real. Yes. Yeah, I still need because I want to define the analog of beta epsilon. So I will define one more set where this expression is bigger than epsilon. Yeah? So the set of the pairs are cross QP such that this expression, and I don't want to rewrite it. This expression is at least epsilon. Okay, is it clear? Yeah, is it clear what does it mean? Yeah, I just don't want to rewrite it once again.
With a limit now, right? Not.
Actually, I think in their result it's lim-inf, yeah. But I think you can put infim on it and you'll be safe.
So is it obvious that it implies that is a generalization?
If you can avoid 0. So when you write lim-inf, you don't care 0, 0 case, yeah? Because it's only one pair. But if you write inf, then you should avoid it.
No, the question is whether this implies. Yes.
Whether, yes. It's not obvious.
It's not obvious, that's what I Is it
It's
supposed
not
to be obvious or is
It's not difficult. I will say about that. Yeah, I will say a couple of words about that. First, I want to state the result. Oh, Okay. Maybe it was. Right. They showed that for every positive epsilon and for every periodic beta in QP, the set med epsilon with beta fixed, so how should I write it? Intersected with R cross beta, right? Something like that. Yeah, has 0 box dimension. So this is the result. In particular, it means that if we in particular, it means that for every fixed beta, the set of alphas for which this may not be true has Hausdorff dimension 0. Yeah. But well, this is slightly stronger than that. So this is what they have, what they proved. Yeah, and also they conjectured that this should be true for every pair alpha and beta. And if time allows, yeah, probably not, but if time allows, we'll see that actually their conjecture is false. And that in this more general case, one can find the pairs alpha and beta such that this is not true. It's bigger than 0. Right. So, of course, it's very interesting to check how does this imply, well, does this imply periodic little conjecture, initial one. And it's...
So say again, the generalized one is false?
The generalized periodic little conjecture implies initial periodic little conjecture.
Yes, but you said that there are counterexamples to the generalized. That's what you said? No.
Yes, there are counterexamples to generalized little
Yes.
conjecture, but it does not does not
Yeah, I understand.
does not
Sure.
follow. It does not. So even more, we will see that they will not produce counterexamples to initial periodic little conjecture. They are very special. They are of very special form. Right. 0 box dimension. So also in their paper, they showed how does initial periodic little conjecture follows from this one. Yeah? I won't prove it. It's not difficult, but I don't have too much time. So they proved, let's call it proposition. If alpha is a counterexample to periodic little, periodic little conjecture, then the following pair, 1 over alpha 0, should belong to med epsilon. So it should be counterexample to generalized little conjecture. I will write it in this way, it's shorter for some positive epsilon. Yeah? So if one can prove that the generalized that med epsilon is empty, then it would immediately imply that the little conjecture follows. But as I said, it's not empty. So at least this short proof won't work. Well, we need something trickier. Right. Okay. So this is how it follows. Right. Now let me slightly move to some more recent results about this conjecture and about the potential counterexamples. So, first of all, this Einstein-Kleinburg result, from metrical point of view, is the best possible. Yeah, so you cannot make Hausdorff dimension less than 0 or something like that. So it's 0, so dead end. So no, you can't improve it, yeah, from metrical point of view. However, one can rewrite this result, and I will show you in a minute how. One can rewrite this result which allows improvement. I won't improve it. I don't know how to improve it, but at least you'll see that there is a potential for improvement there. Right, so we have this proposition. It was proved in the initial paper, but actually some stronger proposition takes place. Kind of.
Do you mean that their methods don't allow you to prove more than dimension 0? Or so I mean, what about sort of logarithmic dimension or something like this?
I won't formulate it in terms of dimension. I will formulate it, as I said initially, in terms terms of combinatorics of infinite words, in terms of complexity. Well, positive dimension, positive Hausdorff dimension means in that case that the complexity grows exponentially, yeah. But you have plenty of other functions which grows slower than exponent and faster than, I don't know, constant. So there you can, if you show that complexity grows, let's say, slower than, I don't know, exponent of square root of something, yeah, it's an improvement. But let me write something. Okay, so. Better proposition, yeah, so more generalized proposition. Proposition 2, yeah. If alpha is a counterexample to PLC, it's the same as there. PLC. Then not only this pair belongs to med epsilon, I would say I need it slightly stronger. So if it's a counterexample to PLC, then we should have some higher steps. We should have some epsilon in our limit, yeah. So the limit should be positive, and we will get some epsilon there as well, yeah. Mm-hmm. So we need it somewhere there. So with the mean, at least some epsilon, yeah. So is it clear what I mean? Because I don't want to rewrite all everything. So this means at least epsilon. Then the following pairs. Alpha n, I will explain what it means, and I also explain what it means. Belongs to med epsilon, let's say star, it's a different epsilon, where the continued fraction expansion of alpha n is an plus 1, and so on. So it starts with an. Yeah? So we kind of cut the beginning of our continued fraction expansion. Yeah? And beta n, again, is given by continued fraction expansion in the following way. an minus 1, an minus 2, a1. So this one is rational, surely, yeah, because continued fraction expansion is finite. It's a rational number, and we can look at it as a p-adic number.
And you assume that a1 and 2 is a continued fraction plane.
Yeah, so yes. So a1, a2, and so on with the continued fraction expansion of alpha.
And what is epsilon star? It's another epsilon.
Yes, well, this epsilon star is defined by this epsilon. I don't remember the formula. It's something like epsilon squared over 2 or something like that.
It's independent of that.
It is independent on alpha, but it's dependent on epsilon. So I don't remember the formula. It's like something like epsilon squared over 2.
But you get this for every end. There's a sequence of counterexamples, right?
Yes.
The question, does epsilon star depends on them?
No.
For every end.
Yes. So we have the sequence of counterexamples. Yeah. So we have this all the sequence of counterexamples, and all of them lie in band epsilon. So all of them lie in very small set. The next thing I want to say is, again, is an improvement of Einstein-Kleinbock result. So in their result, we fix beta and say something about the set of alphas. Yeah. But this result can be improved to the result about the pairs, alphas and betas, independent on either beta or alpha or anything.
Wait, that's a question. 1 over alpha 0, is it in this sequence? Or not? How can
Either it is or it's very or it's very.
I just can't construct it because
1 over alpha is this one, right? So if you remove a1, you should be you should be careful about these, and maybe. So it's very similar to alpha 1, and here the 0 should be very similar to beta 1, yes, because it's integer. Yeah. So here you have some integer, here you have also integer plus alpha 1. Yeah. So I'm not sure that they are equal to each other, so maybe you need to do some manipulations with the numbers to make this pair to be the same as there. Right. Theorem. It belongs to 4 authors: Badziahin, Bujold, Ziegler, and Kleinbock. So, well, it was proven before. It was proven in 2013 or even 12. I don't remember, but it was sent to the journal this year. It's sent, yes. This mad epsilon has 0 Box dimension. Now let's have a look. What does it say about the continued fraction expansion of potential counterexamples to Pettigrew conjecture? So this set has 0 box dimension. This sequence belongs to it. Yeah. And if you forget about beta n's, but just look at alpha n's, yeah, what does it say? That the numbers with these continued fraction expansions, yeah, where we shift this, well, I know, infinite word, or shift the sequence left and left to left, all of them should belong to some set of 0 box dimension. Yeah? this set has is a subset of another set of zero box dimension, so has zero box dimension. And from here one can get, again, it's not completely straightforward, but it's not difficult. If you look at the continued fraction expansion of alpha as an infinite word, then its complexity I'll write it in this way. So limit n tends to infinity. The complexity of WCF alpha n. So the complexity of infinite word means the number of words of length n which are subwords of W. Yeah. So is it fine? So should I explain that? Should I write it down? No. Okay. Oh, it's not p. It's log p. Yeah. Logarithm of this complexity over n equals to 0. Or in other words, that the complexity grows sub-exponentially. So it already rules out a lot of, I would say, the most of infinite words, the most of numbers with continued fraction expansion, because for the most of numbers, the continued fraction expansion will contain all possible subwords, yeah, which is of course exponential. But by this theorem, all of them are ruled out. Yeah, so okay, so we have this.
But do you mean topological closure?
Yes.
Do we know it about that sequence?
That which
about the alpha?
Sorry?
Do we know these properties about the alpha n that you potentially may have from counterexample?
About alpha n, yes. Oh, sorry. What do you mean? Do we know? We can show that every alpha n should belong to the set of zero box dimension, but not only alpha n itself. But if you look at this sequence of alpha n's as a set and take a closure, it still belongs to the set of box dimension 0.
It's not obvious. I don't see how to.
We can discuss it later. Simply because we have closed set somewhere.
We have a set in dimension 2. We have a set in alpha beta.
If you have the set of pairs belong to the set of zero box dimension, then the set of each coordinate belongs to the set of zero box dimension. Yeah. But here, I would say just one very short explanation, but then we can discuss it later. This set is closed. You can check that.
Yes.
Right. So we have that. So if you want to look for counterexamples, then it makes sense to look at numbers which, with the complexity of continued fraction expansion as slowly growing as possible. For example, constant. Yeah? If you look at if it's constant, then this continued fraction expansion is periodic, yeah, and it's also covered. It's covered by the Matano-Tilly. So at least both opposite cases are covered. Yeah, so it should be somewhere in between. But still, okay. So let's go. Just make one step away from periodic sequences, periodic infinite words. Okay, so let me try something. We look for alpha with p alpha n as slowly growing as possible. Yeah, so as slowly growing as possible. if you make one step away from constant, we know that this sequence grows at least as n plus 1. And if it equals to n plus 1, then we have a big collection of words for which it happens. They're called Sturman words. So these Sturman words are kind of the next candidate for counterexample. Right. Now let me, okay, so this was one result. Now let me give another result, another theorem. Again, it belongs to the same set of people, Badziahin, Peugeot, and Ziegler and Kleinbock. The same year, actually the same paper. If, right, let me firstly write it down, and then if it's unclear, I will explain it. So if this word is eventually recurrent.
So what did you say that for Sturmium you can?
Sorry?
What did you say? The Sturmium cannot be counterexample. Can you prove that?
I haven't said it yet. But I will tell that, yes. If it's eventually recurrent, then alpha satisfies periodic Littlewood conjecture. Right. Is that clear? No. Okay, so again, it comes from a combinatoric of words. So what does it mean? Infinite word is called recurrent if every finite subword of this word appears in it infinitely often. Yeah? So if you take any fragment, finite fragment of it, somewhere later you'll find another fragment and another and another. Yeah? By eventually recurrent, I mean that maybe the word itself is not recurrent, but if you cut the beginning of it, yeah, so some finitely many first terms, then it becomes recurrent. So this is what I mean by eventually recurrent. Yeah. So if it is eventually recurrent, then alpha satisfies PLC, and one can show that all Sturman words are eventually recurrent. Yeah. Well, it shows much more than that, but at least you have a corollary. That if alpha is a counterexample to PLC, PLC, then the limit n tends to infinity of the complexity WCF of alpha m minus n is infinity. So it should grow faster than n. And so now, if it grows very fast, it satisfies periodic Littlewood conjecture. If it grows very small, it also satisfies periodic Littlewood conjecture. Unfortunately, there is quite a big gap between n and the exponent. Yeah? So maybe if it grows, I don't know, some polynomially, or like I don't know, exponent to the square root of x, or square root of n, something like that. Maybe you can find a counterexample. But at least two end points, two opposite cases are covered. Right. So.
Do you believe that there are counterexamples?
Sorry?
Do you believe?
No.
You believe in the conjecture, yeah.
There was some period of time when I was in doubt. But now I think it's false. Sorry, it's true. This periodic little conjecture itself is true, but the mixed little conjecture I think is false. And I didn't say anything about mixed little conjecture. If we generalize this periodic norm to something more general, it's false. But I don't want to say about that anything because we don't have too much time. Oh. How goes that?
We need to pull that one down.
I think you have to pull that one down because by pushing it up, and that cable.
Hopefully now it goes well. Okay. At least nothing is seen, so maybe it's fine. So I'll probably in the last 10 minutes. Probably in the last 10 minutes, I will give some brief explanation of the last theorem. It's actually not difficult at all. Yeah? So one can prove it using some elementary things, some elementary arguments. I had more results which I wanted to talk about today, but I think I don't have time for them. So let me just give some brief explanation and stop there. So how can one prove this theorem? Actually, one can do that using kind of dynamics. Yeah, so that's why it's probably interesting. It's probably good to talk here. What I will do. So I will consider. So we usually work with just infinite word, which is constructed from continued fraction expansion. Yeah, and I will add some projective point to it. So the first one is infinite word. This one is projective point, and do the following map. T of WXP is defined as follows. So for this word, it works like a left shift. You know, so it's standard left shift. Yeah, left shift. Here, it's slightly different. So here we take some matrix dependent of the first letter of W and multiplied by XP, where A1 is defined as 0, 1, 1, A1. So we define the following map.
This is acting like fractional linearly on projective point. Like it's just this is going to 1 over XP plus A1. Yes.
Yeah, you can. Yeah,
Okay.
you can think. Yes. You can think about this like that. Yes. Okay. So we have this map. What is good with this map is that if we start with our f of alpha, and here 0, 1, yeah, then it gives us, well, here it's obvious, yeah? So just left shift. And here we'll get as far as either this one or that one. I don't remember. It's probably either this or they swapped. I don't remember. Yeah, and yes, and if you think about it in terms of, I think it's like that. Yes, if you think about it in terms, in terms of projective coordinate, in terms of qn minus 1 over n, this one will give us alpha n. This one will give us, I think, 1 over beta n. But they're closely related to that alpha and beta n from the theorem. Yeah. That's why this is important. At least it's one of the reasons. No more.
Is this some cross section to a flow on SL2R cross SL2QP?
In the paper of Einsiedler and Kleinbock, yes.
Okay.
In what I'm going to explain, we don't think about that.
Okay.
Because I want to be elementary.
Sure,
yes?
sure.
So yeah, now I will give you 3 steps, yeah, and then I will let you go. So the first step, f of alpha is eventually recurrent. What does it mean? It means that the orbit of this word under this left shift should come very close to one of its beginning points. Yeah, so it may be not the very beginning, but if you cut it somewhere, then yeah, is eventually and then Pn f of alpha goes very closely to one of its elements. Is arbitrary close to some of these points. So kind of we have point, then this orbit goes somewhere, and it should go very, very closely to it. Yeah, and whatever small ball we take, it crosses it somewhere. So the first step, so this one is, well, it's just straightforward implication from this definition.
But here you mean n not as big as n?
Vice versa.
Yeah.
So n naught is fixed.
Oh.
N naught is fixed, and then this n changes. Yeah, so we take the whole orbit, and it goes closer and closer and closer to this particular point. And not is some it's some point. It comes from eventual recurrency. If it's just recurrent, then here you can put 1 or even 0. If it's eventually recurrent, you need n0 here. The second step is tricky. So, I mean, here some proof is needed, but I won't give it to you. Yeah, if this orbit comes close to some point, then this orbit comes close to the same point. I mean, to the point with n equals to n0. Yeah, then orbit Tn WCF alpha 0, 1 is arbitrary close to Tn0 of it, yeah, 0, 1. And the last step, I probably won't write it. So what does it mean? It means that this path Qn minus 1 Qn become very close to some fixed pair qn0 plus 1. Yeah, and now we can take in our expression in our limit q equals to I think I should write it because you won't remember that. So the third step, we take q equals to minus q n naught plus 1 qn plus q n naught qn plus 1. So these two numbers are fixed, these are changing. Yeah. So we can make this very, very small periodically, yeah, arbitrarily small periodically. And then if we substitute it into our expression, then the rest will be bounded from above by some constant. Yeah? This shows that the whole expression can be made arbitrarily small. So this very brief outline of proof. Right, one more word. So here, the last result I produced is about kind of the beginning of our infinite word. It shouldn't be eventually recurrent. But if you look at the limit point of this sequence, yeah, they can be anything. So they can be recurrent. You can surely find recurrent words there. You don't know, maybe they can be still Sturmian. Yeah, you cannot say anything about the limit words from this theorem. So the next step, the next attempt to check what can we say about limit words of potential counterexample. And this is what I also wanted to tell you, that these results are even newer than this one. But I'm afraid I don't have time. So if you are interested, then we can continue after coffee break. And now I finished.
Could you give us a flavor of the result on the limit words? I mean, it's
You mean
what you just the thing you just said. So just a flavor.
the most general result is about half page long.
Ah, okay, all right.
Yeah,
well,
so I won't tell you about that. But in particular, it implies quite a lot of particular results. For example, it shows that this limit words cannot be Sturmian. It also covers quite a lot of automatic words.
Any word that occurs as a limit point of one of these words, of counterexample word.
Sorry?
A limit word, sorry, just to get the definition right, is any word that occurs as a limit point of the continued fraction expansion of one of the counterexamples.
Yeah.
Okay.
Then, actually, from there, I didn't have time to mention that. From there, we can find counterexamples to that generalized Einsiedler-Kleinborg conjecture. Because if you look at that limit words, they can be periodic. And if they're periodic, and this xp, yeah, or this second part is very, very particular, yeah, then they produce counterexamples.
I see, and you have some sort of freedom to prescribe that particular second
Yes.
part. I see.
Yeah. Well,
Yes.
I can make them very precise. Yeah, I can write down what they should look like. Actually, there should be some eigenvalues of matrix coming from there, and this matrix comes from a period. So yeah, you can make it very precise. We can cover many automatic words, many, not all of them, many.
So you'll have your periodic word, and then you'll get a matrix which is a product of these, and you'll take this guy to get the Perron-Frobenius eigenvector for.
Yes, yes. But it does not, for example, does not cover Thor-Morse word. So Thor-Morse word is kind of, if someone wants to look for a counterexample, it may be good word, but it's only one. So I'm pretty sure it should satisfy PLC.
Okay.
Yeah, but yeah, I want to say that not everything is covered, so we still don't prove medical conjecture.
But how do you characterize automatic words which you cover?
Again, it's well, it's not too long, but
Yeah, maybe we
Yeah.
can schedule another
Yeah.
talk a little bit
Yeah, yeah.
later.
Yeah.
okay,
Makes sense to have maybe another 1 hour talk where you would explain.
okay,
more
it makes sense,
about
yeah.
it, because it seems like there is still lots of material.
Mm.
So, any other questions?
Method or say some words on the method of the proof. The theorem is dynamical system. It's elementary.
You mean this theorem?
No, the main the first theorem that
You mean the first four authors?
Large-net,
So that part, that proposition which I mentioned, yeah, there was a proposition 2, and the theorem itself. The proposition is more or less elementary. Yeah, so I would say classical analytical number theory, a classical definite approximation. Theorem itself, yes, they follow yes their paper, their previous paper, and they use kind of more advanced Leiden-Strauss result, which was not available when they wrote their first paper. Kind of.
and this tricky business as elementary dynamical proof. Oh.
It's more or less elementary, yes. But it's hard to explain what is elementary, what is not.
No, I meant in their language, in this SL2 language, this has a short proof, and this density of an orbit, or
It's not formulated in the dynamic system.
Is this the part where you calculate, just provide concrete estimates for this calculation?
We can provide yes.
Cross-section. So basically you
The
calculate
natural extension of this map will be a cross section for that.
Okay, another question? Okay, so